We are glad to have Brian KYANJO talk to us about his summer research. This is a research he did during an internship at the Idaho National Laboratory. So I would allow Brian to take over from here and tell us a bit about himself and the research he did during this internship. Thank you.
Okay, thank you, Titus, for the introduction. My name's Brian KYANJO, as all of you know. So today I'm going to talk about the research I did during summer internship at Idaho National Lab. Yeah, I guess you hear me very well. So during the summer of 2022, we worked on a project named Geothermal Closed Loop with Dr. Paulo Balestra and Carol Paris from the C-130 department under the Idaho National Laboratory. So the following is the outline. So I'll take through the introduction, talk about the software coupling, then the mesh generation, then the results, and some conclusion, and then I'll share some PDF to elaborate more of what we did. So what's the motivation about this thing? So basically, when we talk about the geothermal, we basically talk about the extracting energy from underground and then using it either to generate electricity or to generate heat. So this is motivated because we know that to move beyond partial intimate solutions, we need more than wind, solar, and batteries, because we know that as this era, renewable energy is not fully complete, because we can no longer rely on wind because of the seasons. We can't rely on solar because of the batteries that can't really keep enough energy to keep running for the entire year, and the sun in some seasons is not reliable enough. So we need extra renewable clean energy sources, for example, geothermal. So the facts we based on is by assuming that the Earth is a fully charged boundless battery that has renewable source of heat energy and at its core. And this is due to the two factors. One, the primordial heat radiating from the core of the Earth. And this is due to when the Earth was created, like around 45 billion years ago. And also the reactive decay that was created due to Big Bang, when particles were separating. So with this kind of energy that we have underground, if we can extract it by maybe inserting a pipe down and then passing through water and then absorb this energy and bring it back to the surface to generate either electricity or heat for heating facilities, this process is what we call a geothermal closed loop. So basically, geothermal is, in simple terms, just a buried pipe system. So we drill wells underground and then we pass pipes in there, then inject water inside, and then we extract it from deep underground, and then bring back this heat to the surface, and then we transform it into electricity. So this is basically what we did. And some of the tools we used are what I'm gonna showcase as we go around. But basically, the process actually looks like this. It is called a closed pipe because the process is closed. So the pipe is closed throughout so that we can enable what we call the natural convection. Because in what we designed, you can either have forced convection. That's where we are using a pump to pump water to go down, go through the pipes, and then come back up. And they also have what we call the free convection, the natural convection, which is what we call the Simpson effect, whereby water is injected from here, cold water, it comes down. This is our rock. It absorbs the heat, then it comes back with the heat up here. And this heat goes to the heat exchanger, which converts it either electricity or heat that is used for heating. Yeah. So some of the tools we used is FALCON. So FALCON is just the most best application. This is a thermohydraulic mechanical process that we use in subsurface system. It's just an application that is embedded in MOS. MOS is a general code that is designed by Idaho National Lab, and FALCON is one of its applications. So this code can be used for simulating reservoirs, we can effectively use it to solve problems using high-performance computing centers, and it employs a well-defined development and strategy in solving real-life problems. This has been developed by the Geothermal Energy Group at the Idaho National Laboratory, and we couple this FALCON to another code, which we call the RELAP5-3D, which I'll talk about in a minute. So RELAP5-3D code is a fully integrated code that is used to it's used to simulate the thermohydraulic and kinetic capabilities as we analyze maybe fluids, can be nuclear reactors, it can be anything. So this code has also been developed by INL, and it provides fast and reliable robust thermohydraulic description for fluid being injected in a closed loop for our case. But it has also been used to estimate the fluid enthalpy change and low pressure drops as a function of time in several projects that have been designed by INL and other laboratories that are taking advantage of RELAP5-3D code. So this code receives from FALCON the boundary conditions. In this case, we're talking about the thermal heat flask that simulates the rock domain and then runs for a certain amount of time and then communicates back to the FALCON. So this is what I'm gonna show in the diagram. So RELAP5-3D and FALCON software coupling works like this. So this is my software coupling, and this was done under the Python wrapper. So we have our FALCON here at initial conditions T0. So we supply T0 here and initial fluid temperature T0 and enthalpy H0, and then this will run for the time dt FALCON up to final time, and then it produces the final temperature for the rock, which it sends to the solver. The solver in this case is the RELAP3D. So RELAP3D will take in the initial rock temperature from FALCON and then runs for a big time step, DTS, and then produces the final fluid temperature and heat enthalpy, TN. So the process continues like that until we are able to simulate the final fluid temperature of the water at the end of the pipe, because we inject in the cold rock temperature, the cold fluid temperature here, and then we expect to get the final fluid temperature, because when we know the final fluid temperature, then we know the amount of heat that has been extracted from the rock. Yeah, so that was the coupling. So the mesh generation, so because we are looking at spider legs, so the pipes that we drill out after drilling and we sat down, it depends on the number of legs you put in there. So these are the meshes for leg one when we have leg two. So having two legs just means that it's just one pipe up, then it has two spiders down. 3 legs, it means you have 3 spiders. 4 legs means you have 4 spiders, and etc. So these are some of the meshes, and this is a rock domain cutout. You see how the pipe is embedded in the rock, so from the top to the bottom. Yeah, so here we have after the results of the mesh after the simulation. So you can see that for A, B, and C, these are initial temporal variation of the rock temperatures for the 1 leg, 3 leg, and 8 leg configuration. And then the final, you can see there is an invisible line here that depicts the pipe. And you can see that as it goes down, the temperature of the domain of our mesh keeps on increasing as you go down. So red means it's the hottest. So we see our pipe. So this pipe you see here is the one that runs the water through up to the surface, then absorbs heat from the surface, and then it comes back. You may ask yourself, you don't see a pipe that brings back, but I'll show you another picture of our pipe, because our pipe is coaxial after the end of this presentation. So these are some of the results we are able to get, because we are trying to see how many leg configuration we can actually have to get the maximum efficiency in our designs. So this shows the initial fluid temperature for different volumes. I'll show you what we mean by volumes here. And this shows the simulation after maybe a period of 10 years. So you can see that we're able to extract from pushing in water at 280 degrees Celsius, and then we extracted up to 400, around 460 degrees So it's silicious. So you'll see that at first it is actually no difference. So I kind of extracted out this part to show you that as the temperature, as time goes on for different volumes, because these are different volumes in our rock domain, you realize that we have a draft here. And if you see here, when we have like leg 1, leg 2, leg 3, you see that it's almost the same, but at least leg 3 is better than leg 1. So the amount of heat is extracting. But the funny thing is that as you increase to leg maybe 5, you have 5 legs, you have 6 legs, you have 7 legs configuration, it reaches a point where it's almost constant. So however number of legs you use, nothing will change. So we're investigating to see that someone need to drill a pipe that has 16 legs such that they can be able to extract more heat underground? And the answer was no. So you just have to have maybe 8 legs and you optimize the amount of heat you can extract other than using 16 legs. So that's what we are aiming at in this study. And the conclusion was that the more number of legs per closed loop implies the amount of heat that you absorb from the rock. But however, what we have seen indicates that at a certain number of legs, we will have an economic penalty, that even if you have 10 legs, you get the same thing as someone who has 8 legs. And having 10 legs, that means more drilling and more materials wasted in pipes to make legs. So some of the future works by then were to attain RELAP5-3D authorization, because in the study we did, I had to design my own RELAP3, not RELAP3D, but because we know RELAP3D just gives us the thermal properties, thermodynamic properties, like the fluid temperature of the fluid, the heat transfer coefficient. So I just designed my own solver based on energy balance to be able to give me those, because I couldn't get authorization to this code because I'm an international student and it takes almost 6 months to get this authorization. So we finally tested the code on supercritical carbon dioxide, because water seems to not absorb as much heat as carbon dioxide at its supercritical state. So far we have one publication of these results and another publication still underway. Yeah, and what to take home today is like this will enable us to get a 24/7 carbon-free future and renewable and reliable energy supply, and this energy will never stop because we can't utilize the amount of heat that is under the subsurface for at least hundreds of years from now. So this energy will never stop. And it's a secure and resilient electric power supply compared to what we have available. So to elaborate more on what we did, I will go through this also. So basically what I was talking about there was just the general idea, because I didn't want to fetch deep into what we did. Yeah. So basically the pipe that we put underground is coaxial. So this is what we mean by coaxial. So it has an inside pipe that brings back the fluid, and then the outside pipe that takes in the fluid. So this is what we embed in the rock. And to design this, the radius, the diameter of the pipe matters, because it has an effect on the Reynolds number, which is given by the density times the velocity times the diameter, the outer diameter over the viscosity. And because we are dealing with a turbulent flow, so we are observing a Reynolds number between 2000 and 4000 and Reynolds number greater than 4000 for the turbulent flow, because at different pressure levels, it gives us the level of the flow. Is it transitional, is it laminar, is it turbulent? So in our code, we took into account all these ones, and we calculated the pressure drops using this formula where F was the frictional coefficient. So we had the heat transfer coefficient that we calculated using what we call the Nusselt number. This Nusselt number also depends highly on the Reynolds number, and PR is the Prandtl number. So the design of the pipe really matters on how much heat you're going to absorb. So the more the diameter, the nature of the surface of the pipe also matters. So for this case, we use the pipe that is not insulated on the outer part, but insulated in the inner pipe, because the inner pipe brings in hot water. So we don't want it to cool down by the cold water that is flowing down. But the variation in these two temperatures created what we call a temperature gradient that enabled water to be flowing under natural convection. So the ray configuration, we didn't use the boundary conditions. So we use what we call the ray light configurations. So the ray light configurations, we basically send rays into the pipe at its surface. So this ray will go and absorb heat on each surface of the pipe. And this surface of the pipe is simply attached to the rock. So where the ray touches, it's like it's touching the rock. So you absorb this heat. And as you can see, the more ray configuration you have, the more rays you have discretized, the more amount of heat that is absorbed. Yes. And these were our volumes that I was talking about in the other diagram. So these volumes simply are equal to the number of rays. So if you have 10 rays inserted into the pipe, that means we're going to have 10 volumes that are represented. And we're able to use
Brian.
method to. Yes.
Brian, yeah, sorry to interrupt you a bit. Can you zoom in a little to make it bigger?
Oh, sorry.
Yeah,
so,
yes.
Okay, thank you. So these volumes, this is the kind of structure that we use to model our energy solver, because we couldn't get access to RELAP5-3D. And due to energy balance, we're able to generate a conservation equation that we use to act as our RELAP3D to give us the thermal properties like pressure drops, temperature, Nusselt number, and the Reynolds here. And I've already talked about the coupling in the slides. So that's what I had for you today. Thank you.
Okay, thank you very much for this wonderful presentation. So I think it's now time for questions. So if you have any questions for Brian, I think that's more or less like two aspects of the presentation from the slide, and then he went on to the document and gave us some detailed explanations there as well. So if you have any questions, the floor is open now.
Cool stuff, Mr. Brian. Good job.
Thank you, Michael.
Brian, that was a very nice presentation. Good job.
Thank you. Yeah.
Just not really comment, but I know you say you wrote your own or you design your own R. You didn't code, like how fast like that code? How are you trying to parallelize that code or something like that? Just to ask.
Oh yeah. So the code that I designed to replace Relap5 were based on these volumes. So this was not really fast because it was not optimized. So what I did, I had just wrote it in CUDA. So at first I wrote it in Python, and to simulate 30 years, it took almost 10 days. So I had to rewrite it in CUDA, and it was taking at least like a day and a half. Yeah.
Okay.
So I converted it into C and wrote it in CUDA. Yeah.
Good.
Yeah, I couldn't figure it out in KuPy. Yeah, as you had suggested.
Yeah, I remember.
Oh yeah, they wanted results that KuPy was not really coming up. Yeah, so I just converted everything into C and parallelized with CUDA, and it
Good.
just worked so perfect. Yeah, yeah.
Oh, nice. Yeah.
Yeah,
Good job.
Yeah, thank you.
Yeah,
So
Brian, thank you
you
for.
were also talking about, excuse me, you were also talking about the Renault number, and I don't want to.
Yeah.
Yeah.
So
So
yeah.
how does those different regime of the flow affect the capacity or the amount of energy you generate? Like went from to laminar to turbulence.
Oh yeah, so it depends on the Reynolds. So if the Reynolds is less than 2000, we are going to have a laminar flow. So it depends on the initial pressure we inject water with. Yeah. So because in this study we are considering a turbulent flow because we have to inject water at a very high pressure. Yes, we injected water at a very high pressure, and because of this dissection here, this bend here in the pipe. Actually, this is just one leg, but for like 6 legs or 3 legs, we're going to have what you see, this bend here. They're going to be like 3 bends if we're talking about 3 legs, right?
Okay.
So when water comes down here, it's going to be distributed 3 ways. So the pressure is going to be divided. In this kind of so we took this into account because for the tablet flow, we had to change the no-slate number because the kind of flow we choose here highly affects the no-slate number, and the no-slate number gives us the heat transfer coefficient, and the heat transfer coefficient gives us how much heat we're going to absorb from the rock at a particular time. Yeah.
Okay.
Yes. Yeah. I don't know if I answered your question.
Yeah. Thank you.
Okay.
Yeah, Brian, thank you for this presentation. I have 3 questions actually. The first question is mainly on this part which you've shown here. Maybe you can just move it up. The same, yeah. Because you're studying fluid in the coaxial pipe, right? And I'm thinking of a cold material going in and a hot material going out.
Yes.
And how is the efficient? Does it mean how is it insulated? As in, because I'm thinking of.
You're thinking of?
As this is a coaxial pipe, since you have 2 fluids, the cold and hot, as in this cold might influence the steam. It might cool out the steam so that maybe the energy generation maybe might go down.
Oh no, it doesn't, because the inner pipe is highly insulated. Yeah, the cladding is very strong that the same temperature we get from down here is the same temperature I observe out here. Yes. And it's efficient because this is already being done in the oil industry. Yeah.
Okay.
Yeah, so they are okay.
Yeah. And another question is about how this geothermal, as in, since you are directing you're trying to drill on the earth surface, how does it affect the earthquakes? Can it trigger the earthquakes? So
I don't know about that, Kachinga.
Okay.
Yeah.
Maybe let me ask another one. So is it restricted?
Maybe you can explain that. Maybe you can explain that if you know. Maybe you can explain that if you know.
I don't have an answer.
Okay.
Yeah. Maybe another one is it location bound or it can be done anywhere?
Oh no, it depends on the location, because what we were choosing here was like places like Yellowstone, which is already, we know it's already a lava, it's already hot, so we won't have to dig deep to drill these pipes down there. So if you choose places like maybe Alaska, that means you have to dip so deep to get to the rock. So it will be more expensive. Yeah. So it depends on the region. So it's more effective in the regions where it's maybe there was a volcano or something like that, that the rocks are actually easily accessed.
Okay, thank you.
Yes, yeah. Welcome.
Okay, so I think I also have a question. Yeah, somehow you've answered one of my questions because I was wondering how deep the pipe should go in order to achieve your purpose. But well, you've already answered that. Yeah, so another question I have is like, I think you talked about the fact that you get to a certain point that it doesn't matter the number of wells you drill, like you're just going to like get the same amount of heat or something like that. So I don't know, like what might be accounting for that and what is the reason? Is it that maybe there is just this is it that there's just an upper limit on the heat that you cannot go beyond that?
So so what we observed is like, so the more number of legs you bisect. So according to the equation we have here from the energy solver. So this is a conservation equation. That it means that the heat you input must be equal to the heat that is going to be lost. So like heat gain is equal to the heat lost, you get. So, and when we are designing our mesh, because we design our mesh depending on how many legs we have, we get. So the perimeter of these legs must be somehow equivalent to the how can I make it? Like it is made in a way that if I have the big pipe that comes down before bisection, right? Its perimeter must be equal to the dissection of the individual pipes you're making down, so that we don't lose heat according to this conservation equation. Do you get it?
Oh, okay.
So that means if you have more legs, if you have maybe 10 legs, you're going to have a bigger coaxial pipe up, so that you can be able to counterbalance the perimeter for the individual legs you're going to bisect to get the 10 spider legs. So that means at a certain point, what you get when you have 8 legs will be the same when you have 10 legs, when you have 16 legs. Yeah. And there are many other factors that affect that. Yeah.
Okay, so I'm just wondering, so based on what you did, what do you think is the optimal number of legs?
So it was 8.
It was 8, okay.
Yes, according to this diagram. So you see that as you approach the legs, it tends to be equal. So for 9 legs, it will still show nothing. Yeah.
Okay.
Yeah. 9, 10, it will show nothing. Yeah.
Okay, thank you. That's my question.
You're welcome.
Is anybody having question for Brian? Okay, so I guess there are no more questions for you, Brian. So thank you very much. Thank you for your time and your dedication, and we appreciate the time you and effort you made to talk to us. Yeah.
You're welcome.
Yeah. So in that case, if we don't have any more questions, I think we can bring the meeting to an end. Yeah, so thank you, Brian. Great presentation. Yeah, we appreciate it.
Thank you. Thank you, Titus.
Right. Okay, so we bring the meeting to an end. Bye, everyone.